Hi, everyone. It's Tim White. Thanks for taking a second to look over my work for forecasting COVID-19 confirmed cases and fatalities from that Kaggle data set we all used. Um, there's a lot. There's a lot in this, and so I'm obviously going to jump sort of straight to the models, just given the limitation on time. But definitely encourage you to look through some items that I'll mention as I go through. So for my model construction, really where I focused my energy on was on two ideas. So the first was I really felt it was important, and probably we all felt the same, that it was obviously important to get accurate forecasts at the state level. I know the data was at the granularity of the county, but I think the difference between using county level data versus state level data was, over 3,000 different models and forecasts being produced. So in terms of just sheer power, um, and whatever else, I focused my energy on the 320 different regions possible with just looking at the state level data. The other thing that I did was for ETS modeling, I limited the data to start as of April 1st. I think I have a chart of that. Actually, what I might just quickly do is this. Let's go to here. Yes, so confirmed cases, and fatalities had a very similar shape. If I use just straight global aggregation, there's this huge exponential increase up till about April 1st, and then from April 1st onward, over here on the left, it takes on a more consistent trend in seasonality. And so for ETS modeling, I really was interested in just using that time period, because I just didn't think it would handle that exponential increase very well. Whereas an ARIMA model might have, but I can touch on that in a second. So for ETS modeling on that time period, so from April 1st to April 26th, my model results are as follows. So I constructed 3 different models as listed here. The multiplicative model did the best with a root mean squared error of about 12.3 thousand. On the training data, it's not necessarily the strongest, although its root mean squared error is pretty similar to the stronger models, and its AIC and AICC are pretty close. So a graph of the forecast is here. I mean, again, it follows that trend from April 1st, and it sort of carried on through June 10th pretty well. So I think, for short-term modeling, I guess I saw some strength in this, at least at the global level. But again, the interest was how do you then break this down into a state level look? And so I did build ETS models for each individual state, each individual region in that way. A little more difficult to get some visualizations for this, just given the sheer number of models, so the sheer number of visuals that would be associated with this. But what I did try to do is take the root mean squared error associated with each region and take a weighted average of that based on a state's cumulative cases through April 26 relative to global cumulative cases through April 26. And so those weighted root mean squared error values are here. I don't think you can directly compare these to the ones on the global data set, but when I do, some additional discussion on some other state level models I do think those can be more directly compared because they're constructed the same exact way. Fatalities, I took a similar approach with the ETS modeling for fatalities. And again, saw pretty strong results. I mean, I wasn't totally enthused by the fact prediction intervals could go into the negative thousands, but I'm not necessarily sure I'd expect differently from some of the other options I'd have for modeling. So overall here, the root mean squared error was best for just a multiplicative model with no trend. And then for state level data, again, weighted average root mean squared error. So no real direct comparison one-to-one, but these are the results for now. As I went through this, the thought occurred to me that one of the biggest limitations for all ETS modeling, at least as it relates to COVID-19 especially, was it might be good at predicting these sort of leveled off periods, which I think we had a lot of during the pandemic. We'd see these peaks, we'd level off, we'd come down, we'd see these peaks, we'd level off, we'd come down. I wasn't totally, I just felt like there was this risk that the model would be so terribly wrong at some point in time. So the thought crossed my mind that it might make more sense to try to do a random walk model with and without drift. It ended up being the same either way, because then I could do it on the entire training data set, because random walks are just the value of the day prior or the observation prior. And it would actually respond to those increases without breaking the model, and or really respond to maybe renewed spikes of what we saw from March to April. So not perfect. It felt a little bit like a cop-out, if I'm honest, but I really was, again, it's sort of that focus of how do you produce the best forecast at the state level that's usable. On a global scale, this was not useful, but on a state scale, this ended up being actually a little better. And so I employed random walk models for the confirmed case data and got weighted average root mean squared errors of 3.1 thousand on the test data compared to 4.1 with the ETS model. And so I felt a little more enthused by the results that I was getting through the random walk approach. Fatalities, a similar result, a better weighted average root mean squared error than I saw up here. So 248 versus this 441 with an ETS model. ARIMA, I did consider for a second, or longer than a second, I should say. But so if I go over here to plots, this is an ARIMA. I think it was auto-generated. It's a 000110. So nothing sort of on the non-seasonal data, but one seasonal difference, and then first component on the AR, the autoregressive portion of the seasonal data. It honestly performs similarly to the ETS model, at least on the global level. You know, there were remaining concerns of how does that translate to its performance on the state level data. It did perform worse than the ETS modeling. I'll at least point that out, with a root mean squared error of 14.4 thousand versus closer to 12 on the ETS side. So I ended up just sort of scrapping this from consideration further, just because I thought it would sort of muddy my my write-up, but just wanted to mention it. You know, so some conclusions were, for me, you know, the random walk model was definitely the best. Really nothing else to add there. I think what I liked about it was just that, especially for that period in the pandemic where it's still so early, it's going to be a little more quick to respond. So, you know, so if you're running these forecasts daily, you're going to get a good sense from today's cases what tomorrow's cases will be, and I think it just sort of compounded that reality a little bit more. But going forward, I mean, I don't think this would necessarily be the best for later time periods, you know, and I tried to do this, and you'll see that if you read through this, tried to bring in some external data. I mean, it's obvious that government intervention should have had an impact on confirmed cases. I think a little more time would have shown that. Case counts are definitely related to fatalities. You know, so a spike in cases will definitely mean a spike in fatalities, or should mean a spike in fatalities. The issue with this data was it wasn't segmented by age, and age obviously also has that huge impact on whether someone's at a higher risk of dying from COVID. You know, so I think that remains a limitation of the random walk model, and pretty much any model, at least based on the data we have here. So further work would definitely be geared towards incorporating those external data points for a stronger model. But overall, random walk, I was impressed by it. Again, it felt a little like a cop-out. I hope it's not, but I can't really argue with the results I got from it. So anyway, thanks for watching. I look forward to seeing what you put together.